All right, so today we have to give a very sort of easygoing lecture because I understand it's an exam day, so you don't want to be bombarded with completely new ideas, but we need to keep going so we can cover some of the topics on differential equations. By the way, writing the exam and talking about differential equations, I've realized that the course covers way too much material. There's absolutely no question about it. And the only reason for that is because there's only one required math course, and the chances there will ever be two for graduate students is practically zero because our department reduced the requirements for graduation. So having all this material in one course is ridiculous, I can state it. All right, you cannot really concentrate and comprehend all of these things, especially if you never took this material before. But saying that you only covered a fifth of this material and that's your math background, it's also ridiculous. So damn if you do it this way, damn if you do it that way. So please just keep that in mind. I fully understand doing differential equations and linear algebra and maybe a little bit of PDEs in the same course is not the way to go. So we're trying to do our best. And it is very demanding on me as well, okay? Because, you know, I write the exams and it's like, this doesn't fit together. But we have to make it fit. Okay, so we need to talk a little bit about power series methods. So, you know, if you remember, we, especially for computing particular solutions to differential equations, we look at the right-hand side and we said, okay, we have a sine, so maybe we try something that is a times the sine of x plus b times the cosine of x, and it worked, okay? But most of the problems we worked with were simple problems with coefficients in the differential equation that they were constant, or maybe some linear functions of t, or something very simple. So in general, what we will need to do is, we cannot work with sines and cosines and exponential functions. We really can only get solutions in some power series form. And so this lecture and maybe part of the lecture on Monday has to cover the basics of power series methods. Now, the nice thing with power series methods is that they lead to type of solutions that they're extremely important in engineering and physics. And these solutions are identified by the differential equation they solve rather than the other way around. You know, usually we said, here is an equation, solve it, and we got a solution. Now we're going to say, oh, you know what? We're going to have these Bessel functions. But if you ask, what is a Bessel function? You're not going to say it's a function that looks like this. You're going to say it's a function that solves this equation. So quite the opposite thing. So these solutions are going to be looking more complicated, but the equations that lead to these solutions are extremely important, okay? Extremely important in applications. All right, so let me just, as I said, I'm going to try to make the lecture today a little bit light. So we're looking at the power series around some point x0, so they are of this form, okay? And obviously, one of the obvious things that somebody will ask is, does this thing make sense, right? If you start summing a lot of terms going to infinity, do you actually converge? Is this a finite number, okay? So we are going to assume that convergence here implies that on the limit of m that you see there in the upper level of summation, if you take this limit, that this summation exists. It's finite, okay? This is what we will assume that convergence implies. But obviously, when we say convergence, there is a dependence on x0, and then there is a dependence on x. So the question is, what is x0 that makes this to converge, and for what x's does it converge? And we will see the answer to that may not be very clear, okay? All right, Obviously, you know, when I look at this, by the way, when I look at this, if you take x equal to x0, every term is 0. So yes, it converges for x equal to 0. But does it converge for another x? All right, so we will have to see this. So one of the concepts with power series convergence is what's called the absolute convergence. So you are looking in the absolute value of the argument. Okay, so if we take absolute values of this, so absolute convergence means that this series converges, okay, in terms with absolute values. Now, if a series converges in an absolute sense, then the actual series converges as well. The opposite is not true. All right, so we may have some series that actually converge, but they don't converge in absolute sense. But this is a very important still concept of absolute convergence. We're only going to talk actually about one criterion on to verify convergence, especially in an absolute sense, and this is the criterion that is called the ratio test. And so let me describe it with words, right? The idea here is, so we're going to be taking absolute values because we discussed about absolute convergence. So if you have a summation of many terms, you want to be sure things don't grow up, right? And they're all positive terms because we take absolute values. So you want to be sure that none of these terms becomes bigger and bigger and bigger. And a good way to look at this is by taking the ratio of the n plus 1 term divided by the n term. And this is what I have done here. The n plus 1 divided by the n term. And I have written this as, if you can see from x minus x0, you get absolute values of x minus x0. And then you get the limit of this ratio of alpha n plus 1 divided by alpha n that I call here L. I'm assuming that it exists. So effectively, these ratio tests, we will evaluate if this thing grows or not. So can you give me, before actually I release the rest of the slides, what will be a good criterion for this absolute convergence when you look at this ratio? You would like this ratio to be greater than 1, less than 1, you know, what would you like? And this, in some sense, has to do also with the convergence of the series like 1 plus x squared plus x cubed, because incrementally, all right, going from one term to the other, this is what the ratio is. This is what you multiply with. So what would you like to this ratio to be for convergence? What will make sense? Say it again? Less than 1, OK? So effectively, we will call that this series converges in an absolute sense when x minus x0 absolute value times this L, that is the ratio of the two coefficients n plus 1 and n, it's less than 1, and it diverges otherwise. So this is actually the only criterion that I'm going to use in this lecture on power series, and also later on when we do applications to differential equations. By the way, if it happens that this is equal to 1, really you are doomed. There is not much to say. You don't really know if the series converges in an absolute sense or not. So let's do an example. So I'll give you a series. The expansion here, x0 is 2. So the series looks like this, and we want to see if this series converges in an absolute sense. So you take the ratio of the n plus 1 term divided by the n term, and it's just algebra. I see here x minus 2 to n plus 1 divided by x minus 2n. So I have an x minus 2, and then forget these minus 1s. They disappear. I have absolute values. Then I have n plus 1 over n. The limit of that is equal to 1. Everybody can see that, right? As n gets bigger and bigger, n plus 1 over n is about 1. So you get x minus 2 absolute value. So this has to be less than 1 for absolute convergence. And what does that mean for x? It means that it has to be between 1 and 3. So this series converges in an absolute sense when x is between 1 and 3. Let me ask the following. How about x equal 1 and x equal 3? Do these series converge? I'm sorry, I cannot really hear anything.
It says inconclusive.
Inconclusive. Why it's inconclusive? Oh, it says inconclusive. I said on that. Oh, OK, all right. That's what the last slide said, that we don't know, basically. All right, so let's see actually the series for x equal 1 and x equal 3. If I put x equal 1, right, and x equal 3, this is what I get. So basically, you know what you have is, you have an alternating, like, you know, I'm looking here like -1 plus 2, -3 plus 4, -5. Guess what? This series converge, both of them. So actually, the range of convergence in this case, I'm sorry, both, what I said here. So you have -1 plus 2, -3 plus 4. This never converges, OK? So the range of convergence in this case is indeed between 1 and 3, OK? Between 1 and 3. Now, in this case, obviously, you know, you can just look at these two series and see that they don't converge, right? Because each of the terms, really in absolute value, is equal to n, and n grows exponentially. So you can see it, but in other cases, that may not be as simple as that. All right, so radius of convergence, and let me just put all the slides up, all the material. So effectively, we're looking for a range of the values of x where the series converges in an absolute value, and the radius, so half of that range around x0, we call it the radius of convergence, or absolute convergence, OK? So we're expanding around x0. We write a power series, and this rho that defines the interval from x minus 0, x0 minus rho to x0 plus rho defines the range of absolute convergence for this series. So rho is the radius of convergence, and it is such that the series converges in an absolute sense for x minus x0 in an absolute value less than rho. OK? So that's the radius of convergence. By the way, when you do calculations, do not confuse this with the range of convergence, because the range of convergence here, you can see, is 2 rho, but really you're looking at the radius of convergence. All right, and the radius of convergence is basically half of this interval here. OK, so what's the range of convergence of this? How are you going to calculate it? I mean, again, the only thing we know is this ratio test to evaluate convergence. So if you take the n plus 1 term divided by the n term, OK, you get rid xn plus x plus 1n, so you get x plus 1. 2n and 2n plus 1 gives you 2. The limit of n plus 1 is 1. So you get x plus 1 absolute value over 2. So what's the radius of convergence for this? Y is 2. We're taking, you remember the expansion here is around where? What is x0 in this problem? -1, right? Can you see then that the radius of convergence is 2? Yep. All right. Now, in this case, again, the similar situation as before, you wonder, what happens at x equal -3 and x equal 1? Do you actually get, convergence? And if you plug in the values of x equal -3 and x equal 1 to the series, you actually get, you remember the previous example? We had alternating values of it was like 1 minus 2 plus 3 minus 4, etc. Now what we have is, for example, I look at this series. We have alternating values of, let's say minus 1, plus 1/2, minus 1/3, minus 1/4. So in absolute value, the terms are being decreasing, right? So, so this series here converges, right? This series, however, does not converge. Okay? This is the harmonic series, and if you search on the web, on Wikipedia, you will see that that series does not converge. Okay? So the interval here of convergence, if you want to be more accurate, is from -3 to 1, including -3, but does not include 1. Okay, a little bit about Taylor series, right? If that's the most popular power series expansion. So if we have a series expansion around x0, the way you see it here, we say that if this series expansion converges to some function f of x with some radius of convergence rho, then the coefficients are the coefficients that you get from a Taylor series expansion. So it's the nth derivative of f evaluated at x0 divided by n factorial. So that's your regular convergence, basically, of the Taylor series expansion. And if you go the other way and you write a Taylor series expansion like this, the implications here is that all the derivatives of f exists and they are continuous, all right? Exist and they are continuous. And more importantly, if you have a Taylor series expansion, you know what you always do, but you never think about it? You always go and take derivatives of it. I am sure, right? If you write sine of x as a Taylor series expansion, you can keep differentiating without actually being concerned. And that's correct because you can compute all sorts of derivatives from this expansion simply by differentiating term by term in the power series. Now, at least, let me just introduce it from now because I'm going to use it. All the functions that basically have this Taylor series expansion with some radius of convergence rho, we call them analytic functions at x0. So this function here, it's an analytic function at x0. More general, an analytic function would be a function that I can expand in some power series form around x0. And actually, this will be very important because if you can think when we start looking for solutions to differential equations and we take the coefficients of the differential equation, we need to be sure that these coefficients are analytic and we can expand them in a power series form. So that way, we can compute the solution also in a power series form. And I'm going to do some examples of that hopefully today. Okay. Some trivial things with power series. If somebody gives you a power series on the left and on the right, and this is equal to that, can you say with confidence that an equal to bn? Right? The only thing you have to be careful when you say an equal to bn is what? I mean, when you do calculations and homework problems, what is the only thing you have to be concerned to be sure that an equal to bn? The indices have to match, right? So you cannot have an index, for example, that says summation an from n equal to 2 to infinity, and here's summation from n equal to 1 to infinity. So if the indices don't match, what do you need to do? You need to force them to match. Okay? You need to force them to match. Now, obviously, actually, this is going to come also in many cases. If you have a series that is equal to 0, then means that all coefficients have to be equal to 0. If this A coefficients are the same on the left and the right, are the two expansions the same? What's the difference on the left and the right? Is there any difference in the expansion on the left and the right? None. This index n is what we call a free index, right? You can give it any name you want it. So you can call it n, you can call it k, you can call it z. It's the same thing. And obviously, the typical mistake when you manipulate this power series will be manipulating the indices. And it may not be as trivial as you may think. But in this case, these indices, you can change the names. Nothing changes, OK? So changing the index to the summation does not affect anything. All right, so let me take this example, where the summation is from n equal to 2. And I want to change it to a summation over some index that starts from 0. So can you tell me exactly what I need to do? So I want to write this as a summation of some, of an index n, as a matter of fact, because n is dummy. But now I want n to start from 0, not from 2. So what do I need to do? How should we change this index n so that it starts from 0 rather than from 2? All right, so let's do that. So we're going to set m to be n minus 2, right? So when n is equal to 2, this m is going to start from 0 to infinity. So we're going to set m equal n minus 2. So n will be m plus 2. So n will be m plus 2. So the summation will go from m equal to 0 to infinity. an is going to become am plus 2, x to the power m plus 2. And now, you know what I can do is, because the index m is a dummy index, I can change this m back to n, and this is equal to that. And you notice, on the left-hand side, I have a summation on n. On the right-hand side, I have a summation on n. But this starts from n equal to 2, and this starts from n equal to 0. Right? It's a dummy index, so just be sure, and later on when you take other courses with manipulating, indices, even with matrices, just be sure you don't mix indices. But in this case, because the summations are separately on the left and the right-hand side, I can use the same n in these expressions. All right, let me see what we need here. So I want, I have this summation, and I want to change this power here to be x minus x0 to the power n. So obviously, again, I see an n minus 2. I'm going to introduce m equal n minus 2. All right, so I can write this. So I'm going to put where n plus 2. So this will become m plus 4. This will become m plus 3, am plus 2, and xx0 to the power m. And then I can go back to n. Done. Right? And again, be sure, obviously, this is the same as that. But don't go and say this coefficient is equal to that coefficient, because this series starts from n equal to 2. And this series starts from n equal to 0. So that's not the same thing. Now, let's see what we need to do here. So, there is an x squared here. If I can multiply this x squared inside the summation. So effectively, what I can do is I can write this as x to r plus n plus 1, right? And if I what does he wants us to do? It says write this as a where the exponent is x to r n. So obviously we are going to define n plus 1 to m, all right? So n plus 1 equal to m, so r plus m. So n plus 1 again has to be equal to m, so this will become m minus 1, and this will become r plus m minus 1. And then if you want, you can actually rename the m to n. I mean, there's no reason to rename it, but just to emphasize that R and M are dummy indices. And then you can write this series as such. So again, pay attention here that if you have the series multiplied by x squared, that implies that every term in the series has to be multiplied by x squared. So let me do an interesting example, and I'm going to ask you, without looking at the notes, to use your imagination a little bit, okay? So I have, it says assume that this is equal to that. Determine what this implies about the coefficients, okay? Now, I actually realized this 3 seconds before I came to the lecture. I was like checking that the slides are in order, and I look at this and it's like, this is very interesting. So when you look at the left-hand side, can you tell me if there is any relation of what you look on the left versus what you look on the right? Like, they represent a function, right? Obviously, it's a function. Look on the left and the right and see if there is any relation of what you see on the left to what you see on the right. The left seems to be the derivative of what's on the right, exactly. And what function do you know that has that is equal to its derivative? Give me what function is that? E to the x. So when I actually look at this example, because I had prepared the slides a few weeks ago, and it's like, this is interesting. It better be e to the x, otherwise we're in trouble. So when this problem says determine what this implies about the coefficients, they better be the coefficients in the Taylor series expansion of e to the x. And what are the coefficients of the e to the x? What's the nth coefficient for e to the x? Not just one over what? How do you expand e to the x in a Taylor series expansion? Give me the third term, and then you will know what the nth term. So 1 over n factorial, basically. So we better show from this equation that an is actually 1 over n factorial, otherwise we're in trouble. I cannot see how a function can be equal to its derivatives and not being e to the x, right? The question is it the case? And as I said, if it is not, then I'm in trouble. So let's do some calculations. First, to find an equation for an, we need to match the indices. So what I'm going to do is I am going to put n minus 1 to be m. So I'm going to substitute n to be m plus 1. And that's what I have done here. And then I change m back to n. Can you see this? That this is changing the indices and then renaming them. Everybody agrees? Yes? All right. So this then equal to that. And obviously now the summation, the indices match. So I can say that n plus 1 times an plus 1 equal to an. So n plus 1 times an plus 1 equal to an. So I am coming up with a very nice recursive relation. An plus 1 equal an over n plus 1. By the way, with this type of problems, when we look for solutions to equations, we are always looking for some recursive equations that we can use a computer code to actually spell out for us what all of these coefficients are. So in this case, obviously, this recursive equation is very easy. In some other problems, the recursive equations may include multiple coefficients. Maybe here we have only an, but maybe an minus 1 and an minus 2. And in that case, you will not be able to have a nice closed form solution, okay? So you may not be able to do it. So if you take this recursive equation, you assume that you know the coefficient A0. So you can see A1 will be A0 divided by 2. A2 will be A1 divided by 3. And A1 is A0 by 2. So it's A0 over 3 factorial. Can you see that? Right? Can you see that A2 comes to be A0 over 3 factorial? That's 6 there. Similarly, A3 is A0 over 4 factorial. And AN is equal A0 over n factorial. We're lucky. So we get basically A0 times e to the x. OK? So that's a nice example. You could have guessed it, you know, looking at, you know, at the derivative basically to the right-hand side, you could have said that can only be some multiple of e to the x. All right, so let's look at solutions of what is called near ordinary points. So we're going to be looking for equations of this form. All right, this is the second order differential equations that you will have to deal in your exam today. Okay, and but we would like to consider some cases that they're a little bit more complicated than the simple cases we have done up to now, where P, Q, and R were simple polynomials. And in essence, you know, maybe we want to consider any sort of functions as coefficients and still being able to compute a solution to this problem. So in general, we're going to assume that these coefficients are analytic functions, which means I can expand them to some power series. All right? So if I can expand the coefficients in a power series, then maybe there is a solution y in a power series form. And then if I substitute in this equation, maybe I can compute all the coefficients for y in that power series form. So what is an ordinary point? I said we're going to be solving these equations at ordinary points. So the definition is very simple. An ordinary point is a point where this coefficient p is not equal to 0. All right? I mean, that makes sense, right? Because in principle, before what we have done is we divided by p. You remember we had there a little p and a little q when we discussed second order ODEs. Obviously, we're going to have to divide by p, so we're going to assume that there is a point x0, okay? That p of x0 is not equal to 0, and because this function p is going to be continuous, in principle, we're going to assume that there is a little interval around x0 that the function that p of x is not equal to 0, so at least we can compute a solution around x0. I mean, that's the best we can do. All right, so we can compute a solution around x0. Now, let me remind you from the existence theorem for, well, we didn't actually do it for second order ODEs. We did this for first order ODEs. But I can state here that the existence theorem says that if these functions p and q are continuous in some interval, then there is a unique solution to the initial value problem where I specify the displacement y and the velocity y prime. Okay? This is sort of the standard theorem for second order differential equations, and we had a similar theorem for first order. If p and q are continuous functions, then there is a unique solution. So the idea here is, if I have an ordinary point where p of x0 is not equal to 0, and I divide by p of x, this function q over p will be a continuous function in the neighborhood of x0, so we know at least there is a solution. Okay? By the way, even though we know that there is going to be a solution according to this theorem, there is no guarantee that that solution will have a power series form. And I think there is an example that's an interesting example where there is a solution, a unique solution to this problem, but it has no power series form. Okay? All right. So, so basically, we are, we're assuming, by the way, that this original capital Q and capital R don't have any common terms with P, okay? So there are no cancellation terms there. So effectively, with confidence, we can say that Q of x0 is not 0 and R of x0 is not 0, okay? Now, if it happens that P of x0 is equal to 0, then obviously that leads to singularities, all right? So when you divide Q by P of x, and you look at the value of little p of x at x0, this basically goes to infinity, and this goes to infinity. And that's why I said there is no need, we are going to assume that Q and P don't have common terms. I mean, you can imagine if Q had the term x minus x0 and P had x minus x0, they can cancel out, right? So we assume they don't have any common terms. So if P of x0 is equal to 0, then little p of x0 goes to infinity, okay? So this is what we call a singular point. And for singular points, the existence theorem doesn't apply because the functions little p and little q are not continuous. But actually, we're going to be able to figure out if in some particular cases, even though the existence theorem doesn't apply, we will see if we can get a series approximation even near singular points. All right? And actually, we're going to introduce this concept that of points that they're singular, but not very singular. And you will see what I mean when we reach that point. So basically, we're going to assume that somehow the singularity is mild. So even though p of x here equal to 0, somehow we can still solve this type of problems. All right. So we're going to solve first the equation around an ordinary point where p of x0 is not equal to 0. So we're going to assume an expansion that looks like that. All right. So we're going to plug it in there and see what type of information we can actually get. So let me do one example. The best way to learn these things is by simple trivial examples. So let me take y double prime plus y equal to 0. Can somebody tell me what's the solution to that differential equation? And I promise you, the exam today will not have as simple problems as this. So what is the solution to that? Forget the boundary conditions, I mean the initial conditions. So what type of solutions we have? Sine and cosine. Thank you. So the question is, if I do this power series expansion, do I actually get sines and cosines? Now, you may say this is a useless exercise, but if it works for this problem, it will work for any other non-singular x0, for regular points x0, okay? So let me, all the coefficients we had before, the capital Q is missing, there's no y prime, capital P is equal to 1, and capital R is equal to 1. And we're going to do an expansion around x0 equal to 0. By the way, in this case, you can actually do an expansion around any point you want to. All right? But so we're selecting for the expansion to be around 0. But there may be advantageous reasons why you may want to expand around some other point. All right, so we're going to assume y to be given by this nice expression. Obviously, we need to compute the second derivative. So we can differentiate term by term. So this is the first derivative. And notice the summation now becomes from n equal to 1 to infinity, right? Because for n equal to 1, I get, I mean, if you look at this expansion, right, it has a0 plus a1x. Obviously, the a0 term will disappear from the derivative. So I do need to start from a1 terms, okay? So the summation will start from n equal to 1. And then if you take another derivative, you will get n minus 1 and x to n minus 2. So we plug in this in the equation. The equation looks like this. And what do we need to do next? to compute a recursive relation? Huh? Match the indices, right? Because the first index, you notice in the second derivative starts from n equal to 2, and this starts from n equal to 0. So let's match the indices. So obviously, we're going to substitute first n minus 2 to become m, all right? So think of that being x to the m. So this will be m plus 2. This will become m plus 1, m plus 2. And then I rename m to n. And there is my relation. I don't have to do 10 pages of typing equations. I rename the indices here, and the first term became like this. This is like that, so I put all together. And what can I say now about this? With confidence, if this series gives me the 0 function, what can I say about the coefficients? Basically, I can say that this thing inside brackets is equal to 0, all right? And an plus 2 equal minus an divided by n plus 2 times n plus 1, all right? So that's my recursive equation, and now we need to see what sort of functions this recursive equation generates. And now, of course, you guys told me that we're supposed to get sines and cosines. Do we get sines and cosines? Let's see that. All right, so let's calculate first the even coefficients A2, A4, A6. So if you plug in n equal to 0, all right, let's say if you put n equal to 0, you will get A2 minus A0 divided by 2 times 1. And then if you put n equal to 2, A4 will be minus A2 divided by 4 times 3. A2 is already equal to that. So you notice all of these even terms are written in terms of A0, in terms of A0, okay? So effectively, I have one recursive equation and identify a nice formula for the even coefficients. And there is still as a parameter, right, in this power series, A0 comes as a flexible parameter, if you like, okay, A0. So I can do the even terms now also, so I can compute A3. So if I put n equal to 1, so I'm going to get A3 equal minus A1 divided by 3 times 2, all right, that's it. Then I can put n equal to 3, so I can get this is minus A3 divided by 5 times 4, and A3 is equal to that. So I get this weird thing, but it's not really weird, right? You can see here 1, 2, 3, 4, 5. That's a 5 factorial. So this is the even series. And the even series has one unknown parameter there, a flexible parameter, which is A1, right? Which is A1. So let me put those together. So basically, my expansion looks like this. And I have an even part of the expansion and the odd part of the expansion that looks like this. And I'm confused now. What is the sine and what is the cosine? Well, you know what? I can split this series now to the series, the terms that come from the odd terms and the terms that come from the even terms. So this is from the even terms. This is from the odd terms, right? Can you actually see how from here I can go to there and there? Obviously, to split it in two, what have I done also? I mean, I see here the summation, it's from n equal to 0. This n here, it's a free index, right? It's not the same as that n there. So what I did is I took the odd terms, I did renaming of the coefficients, and I get this. I'm sorry, the even terms, and I get this. And then I took the odd terms, renamed them with a new free coefficient n, and I get that. Everybody can see, because these ANs have this nice formula for A2k, and this nice formula for a 2k plus 1. Everybody can see where these things may be coming? And you remember the even terms multiply all of them a0, the odd terms multiply a1. So really what we have done is we have y of x is a0 times this and a1 times that. And you know what that reminds me? Those summations, what actually they are. You remember when you were solving second order ODEs, the homogeneous equation, you will always get what? You will get two fundamental solutions to the null problem, right? So you know what this is? Really, this is nothing else but two of the solutions, two independent solutions to the null problem. That's what they are, two independent solutions to the null problem, to the homogeneous differential equation. Now, again, where is the relation with sine and cosine? Do you see any sign? Where is, oh, there it is, all right? So this is the expansion, the Taylor series expansion of the cosine. This is the Taylor series expansion of the sine. Now, you may say, why bother do all of this to get sine and cosine? Well, because in the process, we learn lots of things, right? We learned that this equation leads to two fundamental equations, y1 and y2. We managed to get this by using a power series form for y and deriving a recursive equation. Here we get the solutions cosine and sine. Now, keep in mind, you don't need to know cosine and sine that they are solutions to this particular differential equation, y double prime plus y equal to 0. But there will be lots of functions that maybe you don't know anything about them yet, that somehow will have a very complicated power series form. And these functions, that they are very famous as cosine and sines, the only way you will remember them is you will remember them from the equation they solve, not how the power series looks like, because there's no way you can memorize the power series form for those equations, okay? They will look too complicated. Things like the Bessel functions, right? We will do this on Monday. You know, if I ask even myself to write down the Bessel functions, I'm going to have to look on Wikipedia on the form of the Bessel function. But if you ask me the differential equation, I remember that, okay? But not the actual power series form. Okay. Let me just finish with this commentary, right? So we computed, let's say, the solution of the differential equation with two summations of the two fundamental homogeneous solutions, y1 and y2. And the summations are n equal 0 to infinity. Of course, we know this is a cosine and a sine, and this series expansions converge. But in practice, there's no way you can say to the computer, go and do the summation from n equal to 0 to infinity, right? So you're going to say to the computer, you know, hopefully stop after a few terms with hoping that somehow this series converges rapidly. So how rapidly they converge? Here is the answer. If you take the expansion of the cosine term, I don't know if you can see it from the plot on the left, if you stop the summation on n equal to 4, you notice, so the dark blue curve, all right, is the actual cosine function. You notice after a little while, for n equal to 4, you don't get good results. It basically, it's far away from the cosine function. For n equal to 20, agrees for, you know, more than one period of the cosine, but somehow still deviates. So actually, if you want to capture the cosine forever, you will need infinite terms. It's all a function of how many periods of the cosine you want to capture, and that will define how many terms you need in the expansion. The same thing about the sine. So the good news is that many of these expansions, they converge very rapidly, so you don't really have to do any summations going to infinity. All right, so you know what? I am going to stop there. And I'm going to continue with this Airy function that has lots of applications in mechanics on Monday, and then discuss a few things about singular points and solving equations around singular points.